All right, so this is the 25th day of Math341. We're going to do a little bit with Stirling's formula. There's 4 different types of convergence. And I was really torn as to how much detail to get into this in class. I've decided, since this is a pre-core 300 level class, I'm not going to go into detail of all the different types of convergence. It's in the book if you really want to read it. We're going to, for the most part, do things a little bit informally and just say it converges in some sense. We'll quantify it a little bit today, but if you were to take an advanced second class, you would do a lot more about the different types of convergence. And this is things where people get really excited about showing, oh, you showed almost sure, I was only able to show weak convergence. All right. Right now, I'm really not going to get into this. Think back to your Calc 1 classes where you had the casual definition of what it means for a function to be continuous, and it was only later that you actually saw epsilons and deltas. For those of you who are coming in a little bit later today, you're not in trouble, but if you would like to pick up a midterm after class, by all means, you're welcome to do so. It is due at the start of class on Monday the 14th. Do not turn it over until you're ready to have the clock start. It's 24 hours to work and then 6 hours for sleeping. Okay? I recommend you don't work for 23 hours and 59 minutes and then sleep for 6 hours and then have that last 1 second of work. Use the 6 hours to be well rested. Okay, who can remind me of what Stirling formula says? Approximately. N factorial is about approximately what is n factorial? Yes? Okay, good. So this is a good approximation for Stirling's formula. Whenever you see something in mathematics, you should always ask, is this reasonable? How could we try to figure out if this is reasonable?
Just check some values.
So one thing is we could start checking some values. Now, if this is what's happening for large values of n, we might have to take n to be a little bit large before this starts to really kick in. And then the ratio of n factorial to this should converge to 1. Now, unfortunately, it could take a while. One thing is to look at how both sides are growing. If I go from n factorial to n plus 1 factorial, how much am I growing by? N plus 1. So I can look here as n plus 1 to the n plus 1, e to the negative n plus 1, square root of 2 pi n plus 1. And if I take the ratio of these two, what should I be getting?
1.
I'm sorry?
1?
Not 1. I should be getting about n plus 1. So does the ratio, converge to n plus 1? And I'm going to be a little bit vague in terms of what I mean by convergence. Is it approximately n plus 1? So this will be a nice way to start getting into our notion of convergence. I think it's clear what we mean from this. So let's look. We have n plus 1 to the n plus 1, e to the negative n plus 1, square root of 2 pi n plus 1. And now we divide by n to the n, e to the negative n, square root of 2 pi n. What's the square root of 2 pi n plus 1 divided by square root of 2 pi n if n is huge? It's about 1. Right? When n is huge, this is really about 1. The error is going to be the square root of 1 plus 1 over n, which is about 1 over n. It's going to be about 1 plus 1 over n. So this is approximately 1. E to the negative n plus 1 over e to the negative n, that's just e to the negative 1. I have an n plus 1 to the n plus 1 over an n to the n. I pull out an n plus 1, and then I'm going to have an n plus 1 to the n over n to the n. That's 1 plus 1 over n to the n, e to the negative 1. Huh. Oh, that's really nice. As n goes to infinity, this is the product definition of e. The product definition of e is the limit as n goes to infinity of 1 plus 1 over n to the n. If I want to do e to the x, it would be 1 plus x over n to the n. And so this does look like n plus 1 as n gets very, very large. This is not a proof that Stirling's formula is correct, but it's at least a good check that this is reasonable, that this is consistent. It also tells you that this e probability really does belong here, and this really is an E. What about the square root of 2 pi? Yeah, it's canceling. So if it's square root of 2 pi or if it's 7, we won't be able to tell the difference. Okay? But E is very different because this has real independence, e to the negative n. The square root of 2 pi, that's just a constant. We're not going to be able to check constants when we're looking at the multiplicative growth rate. Okay, so again, I just really like doing calculations like this. It makes me happy. It makes me feel comfortable with the answers we're getting. Okay, so the 4 different types of convergence that we're not going to really go into is this weak convergence, which is also called convergence in distribution, convergence in probability, convergence in the rth mean, and almost sure convergence. There's also other definitions for some of these things, so some of these things are called other names as well to just maximize the possible confusion. For convergence in probability, you can talk about general random variables. We're only going to look at the very special case where we are talking about comparing to a fixed delta mass. So in general, how should I think of a probability density? It's telling me, if it's a discrete random variable, what the probabilities are that I take on the value x0, x1, x2, x3, x4. If I have a continuous random variable, if I integrate the density from a to b, it tells me the probability I take on a value between a and b. What is the easiest discrete random variable to study? Easiest discrete? Nope, there's something a little bit easier than Bernoulli. So the Bernoulli has 2 options, heads and tails. Yes? The Mobius coin. Right? The coin that is always heads. Right? It's possible that I was feeling in a very generous mood when I was finishing writing the exam last night and I included some problems on the Mobius coin. Unlikely. I think it was as likely as one of the students was going to be killed by the magician, for those of you who were there last night. I'm not going to give you a problem involving the Mobius coin. Why? It's too easy. There's really nothing going on. There's no fluctuations. What we will do is we often want to compare various quantities. And so I want to compare them to a specific number. So for instance, maybe I have a sum of random variables, and I want to compare the average of that sum to the mean. So the situation, or the setup, is maybe x1, xn, iid, rv. Have we used this phrase before? Independent, identically distributed random variables. Okay? It's a great phrase. So rather than writing independent, identically distributed random variables every single time, independent, identically distributed random variables. I could study x1 plus xn divided by n. And so this is the mean. And the question is, what label do we want to use for this? Sometimes we'll write a line over x to represent the mean. This is sometimes a little bit hard to see when we're doing things on the blackboard, but we're at least using the same letter. Sometimes you might use a new letter. Maybe I'll use the letter y. Or maybe I'll call it maybe y sub n to indicate that it's a sum of n variables. Okay? So you really want to think about good notation. So what do you think happens as we take more and more values? We sample our distribution more and more times and we look at the average. What do you think the average should converge to? Yes?
True average of the population.
It should converge to the population average. So assume the expected value of xi exists, and let's say it equals mu. The hope is that x bar, or equivalently yn, converges to mu as n goes to infinity. This is the simplest statement we could be asking. We're just asking that it converges to the mean. We're not really specifying what we mean right now by the convergence. So one possibility might be, I want to know that I'm converging to the mean, and I want to have some sense of the fluctuations about the mean. How far away do I expect to be from the mean with high probability? Is there anything we can say about that? Right? And this is going to lead to, first, the weak law of large numbers. There's also the strong law of large numbers. We're not going to do that. And then there's the central limit theorem. Not surprisingly, the more you assume about your random variables, the more you can claim. The hope is that the more observations you take, the more accurate things become. Right. This is not a political science class. I do not want to talk about the merits of the candidates, but is everybody familiar that there is an election coming up? Okay, excellent. Have you heard that there are polls? There is a lot of shenanigans being done with polls. It's a great way to manipulate statistics. The hope is that the more people you ask, the more accurate your polls are. Can anybody give me a number where you would have a really accurate estimate of what the country will do? Yes?
Approximately 200 million?
Approximately 200 million. So it depends on, I'm not going to even say, I would get into trouble for saying that. So I will leave it as approximately. How would you phrase, where are you getting the number 200 million?
Well, that's actually the Poisson solution type 1. And I'm sampling the entire electorate.
So sample the entire electorate. Sample everybody who will vote. And ask them, who are you voting for? That should be a really accurate estimate of what's going on. It's no longer sampling. It's a complete analysis. So I was actually at a national meeting of Phi Beta Kappa where we were trying to elect somebody, and at some point people were talking about how this is a sample and it's only an estimation. No, everybody's here. Everybody voted. It's not a sample. This is how we actually feel about the issue. Okay? In general, why don't we just sample everybody? I'm sorry, it's impractical, right? It's extremely expensive. So what you wonder is you want to sample a small number of people and build up from that to a true estimate of what's going on. And then the real questions become, how many do you have to sample for this to be accurate? Who do you have to sample? If you go to the national convention of one of the political parties, is this a good place to sample? Years ago, there was a grade strike at Yale, and I was home on winter break, and I saw in the national news that they interviewed 2 random students from Yale asking them their thoughts about the grade strike. It was the president and the vice president of the striking organization. I don't think this was a random sample. Okay? There is a huge amount of theory that goes into how do you sample randomly. How do you take into account that there are subpopulations within the whole population that have different tendencies? How many people do you sample in there, and then how do you try to estimate? So there's a lot of great questions which, if you continue, will be covered in statistics and maybe in some of the psych classes where they do lab design. We're not going to worry about that. We're going to worry about sampling from a fixed distribution where all the observations are drawn from the same thing. And the hope is that the more things we take, the closer it is to the mean. And then later on, we'll talk about the fluctuations about the mean. So I'm going to just write down convergence and probability. So we say yn converges in probability to mu if for all epsilon greater than 0, the limit as n goes to infinity of the probability that yn minus mu is greater than or equal to epsilon equals 0. And here, yn is the mean, x1 plus xn. Okay. Implicitly, I am assuming something here. I'm assuming that the expected value of all the xi is finite and equals the mean. Which distribution has now been eliminated from discussion? There's a huge number of distributions, but at least one of them has a name that we've used in class. What distribution am I not allowed to look at? I heard somebody say it over here. Cauchy. The Cauchy does not have a mean. Okay? It does have a median. It does have a point where half the probability is before, half the probability is after, and that point is 0, and that point sure looks like the mean. But technically, the Cauchy does not have a finite mean. It is eliminated from this. If you want a really good exercise, I suggest you write some computer code tonight and generate 100, 1,000, 10,000 observations from the Cauchy distribution and see, does that converge? Does the mean of that converge? Or does it not? Just because this has the condition that the mean exists doesn't mean that the result only holds if the mean exists. It could hold in greater generality. It might just be the proof is a little bit harder. I'm actually only going to prove the weak law of large numbers in the special case where all this stuff holds. And so now, the weak law of large numbers is that Yn converges to mu in probability. Notation as above. So what this is saying is, as n gets larger and larger and larger and larger, the probability that you are a fixed distance away from the mean is converging to 0. It says nothing about how we're fluctuating about the mean. In many cases, it's going to converge to being normally distributed about the mean. That's going to be a refined analysis later. But think of this as your first choice of what should be happening. As I'm taking more and more samples, my analysis should be more and more accurate. Right? And with higher and higher probability, this should be closer and closer and closer to the true value. And so if I really want to estimate the mean, just take more and more points. This seems like a really good, reasonable strategy. Okay? And all I'm going to assume is that we have a random variable with finite mean. Now, to prove this, the proof becomes a little bit involved. I can make the proof a little bit easier if I assume something about my random variables. I would much rather do a slightly easier proof than to do a more general proof right now. So what additional assumption do you think I want to assume? So we'll assume something about my random variables. What could I assume? What would be a really nice assumption to make? Variance, it exists. Assume variance sigma squared is less than infinity. We don't need this assumption. But if we take this assumption, we can make things a lot easier. We have a situation with a finite mean and a finite variance. Thoughts? Chebyshev. And there's actually going to be a really good colloquium on Monday on Chebyshev polynomials and ways to interpolate functions. And so if you're interested in stuff like this, if you only have a finite number of data points to sample from a distribution and you really want to capture its shape, where should you sample? All right, so we want to prove, all right, so running out of Blackboard space. All right, I assume people will remember that there's a midterm. Usually students don't have trouble remembering that. All right, so proof. Well, let's look at Yn, which is 1 over n x1 plus xn. And again, I'm using this notation because I can quickly look down and see that my random variable is based on n observations. If I used x bar with a line over it, it would be hard for me to look down and see that this involves n observations. If I'm going to use Chebyshev, I'm going to try to apply Chebyshev to Yn. What two ingredients about Yn do I need if I'm going to apply Chebyshev? Its mean and its variance. A lot of these proofs write themselves. As soon as you start asking the right questions and start going down the right path, it becomes natural what to do. If I'm going to use Chebyshev, I need to know the mean and the variance. Let's calculate those. So what's the expected value of Yn? One of my favorite techniques is linearity of expectation. The expected value of a sum is the sum of the expected values. If I multiply by a constant, that just shifts the expected value by that constant. So instead of measuring things in feet, if I measure things in meters, is there really much of a difference? No, I'm basically just multiplying all my numbers by about a third. So this will be equal to 1 over n mu plus mu n times, which is just mu. So what this is telling us is, not surprisingly, the average of the observations, its expected value, is the mean. You would expect this. The question now is, what is the scale of the fluctuations? So now we want to find the variance of yn. What is the variance of a sum? I'm sorry. Good. Since it's independent, it's the sum of the variances. If they were not independent, then the variance would depend on the covariance terms. Think of your random variables as the following. If I look at x minus x or x plus x, these should have very different variances. And if my distribution x is symmetric, x and negative x actually have the same density. In this case, I really understand x minus x extremely well. In the second case, x plus x is just twice x. Okay? So it's essential that we have independent random variables. If I rescale my variable by 5, what does that do to the variance? By 25. The variance is units squared. So if I go from feet to meters, 1 meter is about 1 meter is about 3 feet. So if I'm now going from feet to meters, 1 foot is about 1/3 of a meter. I should now have about 1/9 meters squared. Okay? So this is going to be a 1 over n squared, sigma squared plus sigma squared. I have n sigma squared. I divide by n squared, and I'm going to get mu over n, sigma squared over n. And if we can calculate the variance, the standard deviation is not that far behind. It's the square root. So the standard deviation of yn is sigma divided by square root of n. And now we're at the point where we can begin to see nice things happening. Yn is a random variable, and we've played the game of two questions do you always ask a random variable? What is your mean? What is your variance? The mean is mu, exactly what we want. And the standard deviation is sigma over square root of n. As n gets very, very large, what happens to sigma over square root of n? Goes to 0. So the variance of yn is going to 0. So what this means is yn is getting tighter and tighter and tighter and tighter about its mean. Chebyshev is a weak result, but it holds for any distribution with finite mean and finite variance. So we can now apply Chebyshev. And so if we talk about being epsilon away from the mean, think of epsilon as 10 to the negative 200. Is 10 to the negative 200 a large or a small number? How many people say 10 to the negative 200 is small? Only one person? Okay, a lot more. How many people say 10 to the negative 200 is a big number? How many people say it depends on what other numbers are in play? Right? If I have 10 to the negative 200 factorial, 10 to the negative 200 is huge relative to 10 to the negative 200 factorial. Right? When you talk about the size of the number, it's always relative to other numbers at play. So depending on the units you're using, the actual magnitude could be large or small, and you can have things being swamped into the units. Epsilon is fixed. So when we say convergence and probability, we fix an epsilon, and then we let n go to infinity. Ideally, what would you like to have epsilon do as n gets larger and larger and larger? What would you like epsilon to do as n gets large? You want to keep epsilon fixed. So right now we have a potentially very close presidential election. You want to keep that uncertainty fixed. What would you like to do to that uncertainty? You'd like to make it small. Well, what you can do is then you can just choose a new epsilon and play the whole game again. And then as n gets very, very large, it will work. What you'd love to do is you'd love to have an epsilon that depends on n. I'd like to know not only am I close to the mean, but I'm close to the mean by some absolute distance which is independent, which is going to 0 with n at a specified rate. And that's where the central limit theorem will come into play. In this case where we're assuming finite variance, you can begin to see we could probably allow epsilon to have some independence. And the result will still be true. The weak law of large numbers does hold if we do not have finite variance as well, but I just really want to do the proof in this case. So Markov gave us Chebyshev. Chebyshev is now giving us the weak law of large numbers. So let's apply Chebyshev. So it's like proving your differentiation formulas in Calc 1. You always go back to the definition. Let's say a of x is f of x times g of x. I'm trying to prove the product rule. Step 1 is a prime of x is the limit as h goes to 0 of a of x plus h minus a of x over h. And then I substitute in for a of x. We do the same thing here. So we have the probability that yn minus its mean, right, is greater than or equal to k times its standard deviation. What is its standard deviation? So I could write it as sigma y, and I could write this as maybe, if I want, mu y is less than or equal to 1 over k squared. So this is what Chebyshev says. I can then substitute. I know what the mean of y is, and I know what the standard deviation of y is. And so we would get the probability that yn minus mu is greater than or equal to k sigma over square root of n is less than or equal to 1 over k squared. What do we want k sigma over square root of n to equal? So I'll try. What do we want k sigma over square root of n to be? We want it to be epsilon. We're trying to calculate what's the probability that yn minus mu is greater than or equal to epsilon. So the role of epsilon today will be played by k sigma over square root of n. Because epsilon is fixed, as n gets very, very large, what's happening to k? So epsilon is fixed. So I want k sigma over square root of n to equal epsilon. Epsilon is fixed. As n gets large, what happens to k? Also gets large, right? These have to be equal. Think of it this way. Here's the mean, and I want to be a fixed distance away from the mean. Here's mu plus epsilon. Here's mu minus epsilon. My standard deviation, my step size, is getting smaller and smaller and smaller. How many steps is it going to take me to get to here? I'm hopping in k steps, right? I actually should walk because I don't get credit for my pedometer for hopping. So when I walk, the number of steps I'm going to take, not surprisingly, gets larger as my step size gets smaller if I want to cover the same interval. I want to walk the same distance. I want to walk epsilon, but I'm taking smaller and smaller step sizes. Well, the only way I can walk the same distance with smaller steps is now I just have to take more steps. Okay? So we can actually solve this equation without too much trouble for k. This implies that k is equal to epsilon square root of n over sigma. What is the only danger? Yes? Oh no, what happens if sigma equals 0? I'm giving you a random variable with no fluctuations, and I'm asking you, what's the probability you're within epsilon of the mean? Oh, and by the way, you always take on the value of the mean. Okay? It's not that hard of a problem to handle the case when sigma is 0. Technically, you should be writing here, note sigma is not 0. If sigma is 0, we're fools to be doing this much analysis. We should have stopped a long time ago. Okay? But you just have to be careful. Whenever you divide by 0, you have to be careful. All right. So now we know k equals epsilon squared root of n over sigma. So this implies that the probability that yn minus the mean is greater than or equal to epsilon is less than or equal to 1 over k squared, which is going to be sigma squared epsilon times n. Now, if epsilon is 10 to the negative 200, we're dividing by that, so that means we're multiplying by 10 to the 200, which is a huge number. But we have this n. And so as n goes to infinity, it doesn't matter. Epsilon is fixed. I have some fixed number up top, and this will go to 0. So goes to 0 as n goes to infinity, and that completes the proof. Okay? You could actually prove a lot more. You can start weakening the assumptions. You can even have the variances growing with n so long as they don't grow too rapidly. A question?
Wouldn't epsilon be squared as well?
Probably. Yes. Thank you. And so we could probably let epsilon have some independence, right? What kind of independence do you think we could allow epsilon to have in this case? Yes?
Normal.
I'm sorry?
Just normal distribution.
Well, I want epsilon to depend on n, but I still need this quantity to go to 0. This gives you an idea of how epsilon could grow or decay with n. Could epsilon be like 1 over n squared? Well, if epsilon was like 1 over n squared, this would give me an n to the 4th up top, and this would blow up. So I can't have epsilon like 1 over n squared. Could I have epsilon like 1 over n to the quarter? Yeah, if epsilon was like 1 over n to the quarter, epsilon squared is 1 over square root of n. Flip it, it's square root of n. This is still going to tend to 0. So in fact, as long as epsilon squared times n is going to 0, I'm sorry, as long as epsilon squared times n is going to infinity, I think we're going to be okay. So you can actually get a slightly better result than what I've said here if you're willing to do a little bit more work. But again, right now we are assuming variance. The weak law of large numbers holds even if you do not assume things about the variance, but it does assume something about the mean. Okay. Yes? Yes?
Why doesn't our epsilon already have independence?
No.
No?
No.
It's divided by square root of n.
Where?
When you have the epsilon.
This? What I'm saying is I want this to be epsilon. So if this quantity is epsilon, then as n gets large, k actually depends on n. So if you want, think of it as k is a function of sigma, epsilon, and n. And the function actually is epsilon root n over sigma. So you give me an epsilon, a sigma, and an n, and this tells you what k is for Chebyshev. And because k is growing, Chebyshev's the probability is shrinking. Okay. Any other questions about the weak law of large numbers? All comfortable with weak law of large numbers? Okay. So the Cauchy distribution and the normal distribution both have a really nice property. Does anybody remember the nice property they both share? Yes?
The sums of like multiple distributions are like so
Right. So we call this stable. That sums of independent copies of them have the same functional form. Okay? So there's another distribution which is stable. So it's the Poisson. So the probability, and it has some parameter lambda, the probability that x equals n is equal to lambda to the n e to the minus lambda over n factorial if n greater than or equal to 0 is an integer and 0 otherwise. When you're stating things, it's very important to list all the cases and be clear what you're defining it and where. I'm defining it at the non-negative integers, and it's 0 everywhere. It's a discrete random variable. Okay. We can calculate the expected value of xn, so the expected value of x. We've done this in class, right? We did this using either algebra or differentiating identities. And we get lambda. And I believe the variance was lambda as well. But you can check. Okay? So if there's time at the end of class today, I'll do the calculation again. We were using differentiating identities to do this, a wonderful technique. Okay. Let's look at sums of Poisson random variables. If we can show Poisson plus Poisson is Poisson, then how many summands do we need to really work with? 2. Because then as long as it's a finite sum, I can just do grouping with parentheses. So if I can show Poisson plus Poisson is Poisson, then Poisson plus Poisson plus Poisson is Poisson plus Poisson plus Poisson, which is Poisson plus Poisson, which is Poisson. Right? All right. So, is it enough to just consider the case when the two Poissons have the same parameter? No, because as soon as we then group them, they will have a different parameter. We know by linearity of expectation, the expected value of a sum is the sum of the expected values. So the only way that they would have the same parameter would be if their parameter was 0. And then you can go back and say, well, okay, well, what would it mean if we took lambda to be 0? So then we come over here. Well, okay, if n is greater than 0, it's clear this would just be a probability of 0. And then if n equals 0, what do you think this number would have to be? Yes. It would have to be 1. So if you do take the special case when n equals 0, we would have 0 to the 0. And in this case, 0 to the 0 will mean 1. So this is basically the Mobius coin. This is all the probability is now piled up on 0. Okay? I'm really not going to study the Poisson with parameter 0. Okay? Not that interesting. So let's take two different Poissons. So Poisson sums. So let's say xi is Poisson with parameter lambda I. And so let's let y be x1 plus x2. Okay. This is where I wish I hadn't watched so much of The Magician last night and actually prepared today's lecture. Fortunately, it's just a bunch of algebra. And after you do the algebra enough times, it starts to become clear how you should do it. What do you think we're going to need to be doing at some point in this algebra? Yes? No. What technique do you think we're going to need to do in the algebra at some point? Multiply by 1. Maybe you add 0, but that should be something you should be thinking about as we're doing this. All right? So let's do it. So we're going to use the convolution. So the density of y being n will be the sum of the density of x1 of, say, m, and then the density of x2 of n minus m. Right? I want my two variables to add up to n. This is the discrete version. We've done the integral version so many times, I thought, why not do a discrete version just once? Right now it's a sum over all m, but I should be able to restrict my m. By looking at this one, what do I know about m? Greater than or equal to 0. Because the Poisson has 0 probability of being negative. By looking at this one, what's the largest it could be? Is n. So we know we have this range, m goes from 0 to n. Right? And so this is the same as the sum, m goes from 0 to n. The first density is going to give me a lambda 1 to the m. And then I'm going to have an e to the negative lambda 1 over m factorial. And I'll have a lambda 2 to the n minus m, e to the negative lambda 2 over n minus m factorial. Okay? Now, if it's going to be a Poisson, it's going to be a Poisson with parameter lambda 1 plus lambda 2. Well, I've got an e to the negative lambda 1 and an e to the negative lambda 2. That's looking promising, right? So the fact that we think it's going to be a Poisson, we have some hope. So this looks like it's an e to the negative lambda 1 plus lambda 2. And now I'll have a sum. M goes from 0 to n. I have a 1 over m factorial, a 1 over n minus m factorial, lambda 1 to the m, lambda 2 to the n minus m. Right? And it was suggested earlier that we should be multiplying by 1 at some point. This is probably a good time to multiply by 1. Does anybody see a place where 1 might be useful? Yeah, we've got an m factorial and an m minus m factorial. What would you love to have up top? Yeah. So let's combine them. Oh no, I don't want an m, I want an n factorial. And now I can't just multiply by n factorial, I have to divide by n factorial. Well, n factorial has no m dependence, so I might as well put it outside. This is really looking like a Poisson now, right? We have the e to the negative lambda 1 plus lambda 2, an n factorial. All that we're missing is lambda 1 plus lambda 2 to the n, right? That's what it would have to be, because we know if it's going to be a Poisson, because the expected value of a sum is the sum of the expected values, the only Poisson it could be is a Poisson with parameter lambda 1 plus lambda 2. So having a sense of what the answer is really guides us. So all we have to do is show that this is lambda 1 plus lambda 2 to the n. Well, what's nice is the algebra is suggesting itself to us. Question? Okay. So the algebra is suggesting itself. We believe it's a Poisson. It's looking a lot like a Poisson. The only thing that looks a little bit off is this sum over here has to be lambda 1 plus lambda 2 to the n, because we know the only Poisson it could be is the one with parameter lambda 1 plus lambda 2. So somehow we should be able to prove that this is true. Why is this true? Binomial theorem. So therefore, we get Fy of n, for your information, is lambda 1 plus lambda 2 to the n e to the negative lambda 1 plus lambda 2 divided by n factorial if n greater than or equal to 0 is an integer and 0 otherwise. And so this proves Poisson plus Poisson is Poisson. So Poisson is another stable distribution. Okay. Any questions on this? So you can actually use this result to prove Stirling's formula. This is a really nice corollary. Now, unfortunately, the corollary does have a little bit of a prerequisite. I need the central limit theorem. So we will prove the central limit theorem later. What the central limit theorem says is sums of independent copies of random variables converge to being normally distributed. We have to take into account what the mean is. We have to take into account what the variance is. Okay? What do you think sums of Poisson should be? I'll accept two answers. What should sums of Poisson be? Poisson. We just proved sum of Poisson is Poisson. But what should sums of Poisson almost be? What should sums of Poisson almost be? Normal, right? The central limit theorem says sums of Poisson is almost normal. So here's a way to get Stirling. So CLT and Poisson implies Stirling. Now what's really nice about this is when we had Stirling's formula, which was the most mysterious part of the formula? Which part seemed really strange?
The square root of
The square root of 2 pi, that seems strange. I hope I was able to justify at the start of class today E. I'm just really inspired by the magician I saw yesterday, and I'm trying to just have these things magically appear, okay, without killing students or forcing them into embarrassing circumstances. Do you all agree that E was reasonable? I gave you some motivation as to why there's an E in Stirling's formula. The square root of 2 pi, that seems strange. Can anybody think of anything that has a square root of 2 pi in it? The density of the normal distribution. That's where it's coming from. So let's say each xi is Poisson with parameter 1. Let's let yn be x1 plus xn. This is going to be Poisson with what parameter? What should this be? Poisson with parameter? I'm sorry? N. What's the expected value of yn? N. And the variance of yn. Each one of these has variance 1. And this is where I am so lucky I don't have to worry about, is the variance of a Poisson with parameter lambda, is it n, is it lambda or lambda squared? Because each one of these I know is 1, 1 squared is 1. I now have n of them. So the variance is n. Okay? So by the central limit theorem, this should be converging to a normal. I haven't standardized my random variable, so it's not going to converge to a normal with mean 0 and variance 1. What normal is it going to converge to? Yn converges to a normal with what mean? We're running out of time. What mean? N. What variance? N. So if I want to estimate, so here is my normal. Here is n minus a half. Here's n plus a half. The area under this curve should be approximately the probability that yn takes the value n. So this is approximately the probability that yn equals n. Right? Because I have to worry about discrete to continuous. The Poisson is only taking on values at discrete sets. So if I integrate from n, oh wow, bad notation, n minus a half to n plus a half, the area under that should approximately be probability of yn. What is the probability that a Poisson with parameter n equals n? It's lambda to the n, e to the minus n, divided by n factorial. Right? Is everybody able to see down here, or is this too low? I'll do it up here. This is just too good not to see. N to the n, okay, e to the minus n over n factorial. And this should be approximately equal n minus a half to n plus a half, 1 over square root of 2 pi. Now, what's the variance? N, right? Integral of e to the negative x minus n squared over 2n dx. We are running out of time. Does my function change much over this interval? No, thank you. So I'm going to approximate this with just putting in a 1/2. All right? So this is going to be an interval of length 1 times 1 over square root of 2 pi n. Oh, wow, 2 pi n, so nice. E to the negative, this is going to be roughly something of size 0. Right? Because look, by fluctuations, I go from n minus half to n plus a half. This is going to be like plus or minus a half up here. I'm dividing by 2n. It's a really small number. It's approximately 1. If you want to expand this and get more terms in Stirling, go for it. But it's approximately 1. So we now get n to the n, e to the minus n over n factorial is approximately square root of 2 pi n. And so magic, n factorial is approximately n to the n e to the minus n square root of 2 pi n time to go home. Here we go. Okay? So this is a wonderful consequence of what we've been doing. There's Stirling.